Welcome to Physics 2, Lab 5, which is magnetic braking with Faraday. My introduction. In this lab, we were tasked with taking a roll of aluminum foil and dropping a bar magnet through it. The north side is put in first to induce a current from the aluminum foil, and we use our phones to video the experiment and got an accurate change of time between when the magnet was dropped into the tube and when it appeared out of the tube. A preview of my main result. The normal time for the magnet in free fall was about 0.2134 seconds in the air. During the experiment, we found that the magnet took 1.16 seconds to fall down the tube, and after doing my computational model, my results showed that the magnet took 1.244 seconds to fall through the tube. The procedure that my lab group took for this experiment was we dropped the bar magnet in the top of the tube with the north pole facing into the aluminum foil, and then we calculated the change in time from when we released the magnet at the top to when it appeared at the bottom of the tube. These were the models and principles used in the experiment. Magnetic field of a bar magnet to show that it would induce a current from the aluminum foil. Newton's third law of equal and opposite forces to show that the velocity of the bar magnet in the tube was constant. Faraday's law, which is EMF equals number of turns in a coil times the change in flux over time. And then Lenz's law, which is the negative sign in front of the Faraday's law, which is highlighted in red. So these were the formulas used. On the left-hand side of the paper, that is the top left formula is the formula for a magnetic field of a bar magnet at any location that could be perpendicular or parallel or neither. And then the absolute value of the change in flux is EMF, and we used the EMF to find the current. And then we used the current to find the absolute value of the force on the loop from the magnet. And because of Newton's third law, forces are equal and opposite. And then we continued and said that the force of gravity is just the mass times the acceleration constant. And we calculated the final velocity and the change in distance. This is a model of the experiment. And as you can see, we dropped the magnet straight down through the tube. And on the right-hand side of the slide, this is the first section of my code, which shows the initial conditions of the experiment. So on to the actual code. Part 2 of the code shows how I calculated the magnetic field of the bar magnet. Part 3 shows the change in flux over time of the bar magnet. Parts 4 through 6 were used to find the current of each ring and the magnetic field at each ring, and then calculate the magnetic force on the magnet from all of the rings. Parts 7 and 8 were to find the net force on the magnet and then show how it changes in the computational model through time. So this is the result of my coding section. As you can see, the red rings are the visualization of the bar magnet inducing a current on the aluminum foil, and the blue line is the aluminum foil inducing a current on the bar magnet. They are equal and opposite because nature wants to remain in equilibrium. On the right-hand side is my velocity versus time graph. The horizontal velocity line shows that the velocity of the bar magnet in the tube was constant. At the beginning, the dip in velocity shows the magnet entering the tube and establishing equilibrium, and at the end of the velocity, when it decreases severely, is when the magnet exits the tube. The analysis. So possible sources for why my computational model is different from my experimental model is that the cardboard, being a thick insulating layer separating the aluminum foil from the magnet, may have affected the aluminum foil's strength, and another source of error could be an inaccurate value calculated from Lab 3, and another source of error could be human error from timing the fall of the magnet from the experiment. So this is my discussion and conclusions. What if the resistivity of the conductor were as close as possible to zero? How would the dynamics of the falling magnet change? I said, due to Ohm's law, the force would likely counteract the gravitational force almost completely, and it would not be able to fall through the foil at all, giving it a zero velocity. And what if holes or slots were cut into the tube? How would this affect the ring currents in our model? I said that the current would be interrupted by the holes, decreasing the amount of loops. The magnetic force would decrease in magnitude, and the magnet would take less time to fall.